All right, I'm just going to finish off these last few examples we didn't manage to cover today when we're looking at area for polar curves. So here we're trying to find the area of the region that's inside the circle, r is equal to sine theta, and also inside the petal curve, r is equal to 2 sine, or sine 2 theta, rather. So that means we need to find these two areas. They're symmetric, so we can just find one of them. To start off with, let's find the intersection points of the curve. I've started off just by finding the intersections of type A, meaning f of theta is equal to g of theta. But we did see in class that there are different types of intersections that we can have. So this is the type A, where we're just setting the functions directly equal to each other, plus, multiples of 2 pi. But then we can also have the type where we use the property of polar curves, where negative r theta is equal to r theta plus pi. We have to kind of consider those types, and then also where they go through the origin. So it's a little tricky, but we can get this, especially if we're given the graph. Although once we go through this example, I'll show you how you can graph these from scratch to see what's going on. Okay, so solving the equation where we just set them equal to each other, and then factoring, setting both to 0, what we get is that theta can be 0, pi, 2 pi, pi over 3, or 5 pi over 3. So let's see what's actually going on here. If we look at, what I'm going to do is I'm going to just copy this graph, because there's something kind of interesting going on. We can't just go straight ahead and let's just duplicate and try to say, oh, outside, inside, whatever, because the outside and inside graph changes. So if we're looking at this area, I'll do it in 2 colors. We can see that we've got this part here where if we're drawing a line starting from the origin and moving outwards, in this portion, the integral is just, let me just see something. Yeah, there the integral is just the circle. Because we can see that the petal curve is fully outside. And then at this angle here, it switches over to us actually just integrating the part of the petal. So that's the second part. No, that's not a good arrow. Okay, let's see. Here, the area that we want is just the petal. So we're actually going to calculate 2 different integrals and add them together using these intersections. So let's see, what else do we need to use here? So if we draw out these angles, we had that intersection at pi over 3. So let's say this pi over 3 corresponds exactly to where we're dividing up our area into 2 pieces. Then the next part of it starts at pi over 3 and then goes to wherever this is. And it turns out that's pi over 2, but we're going to check here. The petal starts and ends where sine 2 theta is equal to 0. This is when theta is equal to 0 to when theta is equal to pi over 2, because then you get sine of pi, that's 0. And so that means that the total area I guess of this region, we've first got from 0 to pi over 3, where it's just the circle. Oh, so sine squared theta. Then we've got 1/2 pi over 3 to pi over 2, where it's just the petal, so that's sine squared 2 theta d theta. And so then that means the total area, both regions, because of symmetry, it's going to just be 2 times that, so we can get rid of the 1/2. But the key point here really, and you know, maybe I'll copy that graph down again, just to really, I don't know, hammer it home, because I've got extra time here going through it, is that if we're looking at this area and we're thinking about like, oh, outside minus inside, here we're only hitting that graph of sine theta until we hit that angle pi over 3. And then, you know, the only curve that we look at as we, you know, draw these little kind of lines to determine what's inside or outside, you know, this is only sine 2 theta. That's kind of the key point here, is realizing that we have to divide that region into 2. We can't just say like, I don't know, like top minus bottom or outside minus inside. It's like, oh, it turns out it's both inside. On the other hand, I guess if we were to want to compute the area between let's say that this one here this area would be equal to 1/2 from 0 to pi over 3, the petal squared minus the circle squared. And then inside is, oops. And again, we can determine what's on the outside or on the inside by taking our pencil, starting from the origin and seeing what you hit first versus what you hit second. Inside is always going to be what you hit first, then you travel through the region, and what you hit next is the outside. So it's just kind of similar to what we were doing when we were looking at like the volume method with washers. There's some similarities there. For this past question, if you'd like to know how to sketch it, I've got that kind of worked out here. If you don't remember like exactly what these curves look like. So, you know, you can try that out too. Then here, got another example. Let's find the area of the region inside the cardioid. R is equal to 4 minus 4 sine theta, and outside the circle R is equal to 6. We've got the sketches here already. Let's try to see what this region is. So inside the cardioid and outside the circle, you can see the circle is in red, the cardioid's in blue. Outside the circle, inside the cardioid is this region here. Okay, so in order to figure out what this region is, we already know that if we're starting from the origin and moving outwards, we can see that the outside curve is the r theta is equal to 4 minus 4 sine theta. And the inside for this whole region is r theta equal to 6. So we just need to find the intersection points. Now, because we have the graph, we can expect to just find the 2. So we know that we don't really have to check for like too many different types. We don't have to see when they're both 0. It looks like we just have these 2 intersection points. So let's see what we get. 4 minus 4 sine theta is equal to 6. Subtract 4 from both sides. We get negative 4 sine theta is equal to 2, which means sine theta is equal to negative 1/2. Thinking about the unit circle, that gives us like these 2 angles. So theta would be 7 pi over 6 and 11 pi over 6. Then that's all we really need for this one. So here our area would be 1/2 the integral from 7 pi over 6 to 11 pi over 6 of, so outside squared minus inside squared. So 4 minus 4 sine theta all squared minus 6 squared d theta. This is going to be a trig integral again, where we've got like a sine squared. So I'm not going to work it out now. You should get 18 root 3 minus 4 pi. I'm going to say that's an exercise. You really need to use your unit circle, I think, in this chapter. So it's good practice. Let's do another. So we want to find the slope of the tangent line to the polar curve. R is equal to 1 plus 3 cos theta at the point 5 over 2 pi over 3, where this point is in polar form, not like a xy point. Okay, well, we're given this graph. We don't really need it here. I'm just including it here just for fun. But let's do this problem. So we did one in class like this. For finding the slope of the tangent line, we want to turn our polar curve into a parametric form. For that, we use that x is equal to r cos theta. Here, r is 1 plus 3 cos theta. So we go 1 plus 3 cos theta times cos theta. And then y is equal to, or actually I'll expand that out. Let's see. That gives us cos theta plus 3 cos squared theta. And then y is equal to r sine theta. So that's 1 plus 3 cos theta sine theta. So that's sine theta plus 3 sine theta cos theta. So that's sine theta plus 3 over 2 sine theta cos theta. And I'm writing like that just so that I can get it into this form where we have it as 3/2 sine 2 theta. I'm just doing it that way so I can avoid using the product rule later. So from that, we can say that our slope m, so dy dx, we know that's the derivative of y with respect to theta and derivative of x with respect to theta. derivative of y, oops, I forgot the theta. Okay, derivative of y, we get cos theta plus 3 cos 2 theta. And derivative of x, we get negative sine theta plus 6 cos theta negative sine theta. Then at theta equal to pi over 3, m evaluated at pi over 3. If you plug that in, I'm not going to do the intermediate steps. I'll just let you know you should get 1 over 2 root 3. And that's all they want for this question. They just wanted the slope of the tangent line. But what we can do, just for fun, if we want the equation of the tangent line, we need to find the x and the y coordinates. So x, again, it's r cos theta. So that's 5 over 2 times cos pi over 3. So that's 5 over 4. And then y is equal to r sine theta. So 5 over 2 times sine of pi over 3. So it's 5 root 3 over 4. And so the equation has the line y is equal to 1 over 2 root 3. X minus 5 over 4 plus 5 root 3 over 4. I guess that got cut off here in my graphing thing from Desmos, but there we go. That's the tangent line we're dealing with. Now we can do one more area problem. Here we want to find the area of the region that's inside the circle r is equal to cos theta and inside the rows r is equal to cos 2 theta. That's kind of similar to that one we did before that was for sine.